Hello friends, I am Nikita and you are watching Prepare for GATE. Communication has always been an important subject in GATE examination. Every year 8 to 10 marks questions come from analog and digital communication. The syllabus for communication in GATE examination comes from random process, analog communication, information theory, digital communication, fundamentals of error correction, timing and frequency synchronization, and ISI and in its mitigation, basis of TDMA, FDMA and CDMA. Moving on, let's see the topics to be discussed in this lecture will be radio signal and processes, autocorrelation and power spectral density, noise and its property, filtering of random signal through LTI systems. Now, what is random signals and random process? By definition, random signals are those deterministic signals whose succeeded value at any instant of time is unpredictable in nature. Thus, we say that it is not that their existence is random in nature. However, they are there and very much deterministic, but whatever the next value they'll show, that is unpredictable in nature. For example, the temperature. If we consider a particular hour in a day, suppose at 12 a.m. in the morning, then it could have a various range of temperatures. Stock market, inflation rates, etc. are some of the examples. Now moving to a random process. It is defined as an ensemble or collection of time functions together with a probability rule. We'll see further what actually a random process means by this statement. Moving next, here I have shown a pictorial description of how a random signal, being deterministic in nature but still random, can be predicted along the course. This you can see a noise which for a lay person is just like any other signal distributed over a time axis. Here it says that I am a random signal. Right now I am not deterministic. By deterministic he means that he doesn't know exactly what his properties are and how he will behave in future. So he doesn't know much about himself. But with the present time tools, one can easily find with the help of the probability density functions such as Poisson, normal, Gaussian, to get the information content or the error content a bit shows. So this could be an easily illustrative procedure pictorially, which can help you to understand what actually a random process do. Let's take an example. I have shown in these graphs the temperatures of a particular day on 6th and 26th of July 2016 and 17. From the graph, we can illustrate that X is a random continuous signal showing average distribution of temperature on a day for the month of July in year 2016 and 17. Here x1 and x2 are the outcomes of the same experiment performed yearly. Thus, x1 and x2 can be termed as random variable. Mathematically, a random variable is one of the outcome of a sample space or ensemble. However, the vertical line on 6th and 22nd day shows particular value, that is x1 t1 and x2 t2. x2 t1 and x2 t2 corresponds to a particular sample function x1 t and x2 t. Thus, in caps actually x1 and x2, where S is an outcome of an ensemble. Thus, we can conclude here saying a random process maps the experimental outcome into a real functions of time. The collection of time functions is known as ensemble, and a member is called a sample function. Thus, I hope. Let me explain you with one more example that a random variable is random, but it have a probability associated with it. Suppose if we throw a die, we can get 6 outcomes, 1, 2, 3, 4, 5, 6, and each having a probability of occurrence as 1 upon 6. When we map this probability to one of the events occurring in nature, that is time, then it will become a time function of an ensemble process, and this whole process of mapping a random variable, a mathematical outcome, to a real-time function is known as random process. So friends, I hope you liked and understood what random process is and the explanation I told you. Kindly read the example very carefully, as it will clearly resolve your issues. I have given this example in such a manner that it will help you to know what random process is, because it takes a long time for me to understand what a random process was in my engineering days. So moving on, a random process constitutes an infinite collection of random variables. The uncertainty lies in finding the behavior of outcome. Once the sample function of the experimental outcome is known, all the randomness is gone. In communication, most of the random signals shows the property of stationarity and ergodicity. We'll be discussing stationarity and ergodicity later in the slides. What actually a stationary random process is: a random process whose statistical characteristics such as mean, variance do not change with time. However, a non-stationary random process is not that strict in nature. It may have one of its statistical characteristics changing with time or with the time difference. We also know that stationary random process shows some behavior or same behavior from -infinity to +infinity. Stationary processes are more stricter than wide-sense stationary. However, the converse is not true, except for the Gaussian random process. All processes in nature are not stationary as they have a start and an end point. What I mean is they do not start from minus infinity and goes up till plus infinity. A strict sense stationary and a wide sense stationary. What they actually means is a strict sense stationary, a random process x of t is called strict sense stationary if its statistics are invariant to a shift of origin. The process x of t is SSS if the function x of 1 up to x of n. Okay, these could be the outcomes for a time instant t1 to tn will be equals to f of x, x1 to xn, but there is a shift in the origin with t1 plus c to tn plus c. Thus, this shift does not impact a strict sense stationary function. However, a wide sense stationary is a process which is not stationary in strict sense but have a constant mean value and an autocorrelation function that are independent of the origin. What we mean by mean value is that its expectation of WSS random process is given or is calculated by this formula. An autocorrelation function is calculated by this formula. Autocorrelation function is the multiplication of signal itself from its time shifted function. X of t is being multiplied with x of t, only the difference is in the origin. Calculating the time average, mean and autocorrelation. In communication, we usually take those signals whose time average mean is equals to ensemble mean. That means if we calculate mathematically, then also its mean is same, and if we take its time average, then also its mean is same and equal to the ensemble mean. Here I have shown you the mathematical formula for a random signal. X for a random process x of t. Limit t tends to infinity from minus t by 2 to t by 2 x of t dt. Rx t1, t2 is limit t tends to infinity from minus t by 2 to t by 2 xt plus tau dt. Here, the ensemble mean should be equal to the time average mean. What we calculate in communication is mu of x. Expectation of that mean value will give me expectation of the time average mean is limit t tends to infinity minus t by 2 to t by 2 expectation of x of t dt. This expectation of x, if calculated mathematically, will give me x of x into p of x, that is outcome into probability of outcome. That will be equals to mu of x. And this is the value that we calculate to get our mean in communication. X bar is the DC level of the signal that remains constant. Moving on. What actually an ergodic random process is? Ergodic random process are those whose time average are same for all the sample functions and equal to the corresponding ensemble averages. what we mean is, thus is that okay, suppose there is x of t is equals to a and a cos function where a is a random variable. So for any instant, if we calculate x1 of t, then a could have a1 value, a2 value, and okay, yeah. So a could have a1 value, a2 value, and so on. Thus, it won't be having the same ensemble mean as that of time average. We calculate it from minus infinity to plus infinity. Thus, in such scenarios, it won't be a random process. Okay, this is the property which has to be followed by a random process. A stationary x of t is called ergodic if its mean x bar, which is time average, is equals to mu of x, that is ensemble average. We can see that a random process, if from this graph we can actually see the random process, the white and stationary process, the stationary process, and the ergodic process. Ergodic process can be a stationary process too, a wide sense stationary process too, and a random process. However, a strict sense stationary can be a wide sense stationary, but the reverse is not possible. Moving on, the autocorrelation of WSS signal. Here I have tried to resolve first the mean of a WSS signal, and then we can calculate, then we have calculated the autocorrelation function. So you can pause the video and look how this is being performed mathematically to have a better understanding of WSS signal. This is actually the autocorrelation function. If here the a and a square would have been a random variable, then this process won't be a random process. However, in this scenario, a is a constant, then we can take it as a constant, and the Rx t1 and t2 value is equals to a square by 2 cos omega ct tau, where tau is the time difference. Moving on to the properties of correlation, that is autocorrelation and cross correlation. There are three main properties which you can see on the slides. We always take Rx tau to be an even function. Then its property Rx tau will be equals to Rx minus tau. Rx tau will be less than Rx 0, and Rx 0 is equals to x square. Similarly, for cross correlation, to calculating power spectral density is an important property in communication. Power spectral density is calculated in frequency domain. This was derived from Wernicke-Inchin theorem, that if we do a Fourier transform of R of t, we'll get power spectral density, and if we take the Fourier transform of S of x, we'll get the autocorrelation function. In frequency domain, to calculate with the help of mathematical tool, we can calculate it with this formula. And to calculate in time domain with the help of power spectral density, we can calculate in this form. For Rx of 0 is e into x square of t. Okay, which is 1 upon 2 pi from minus infinity to plus infinity, which will be plus. Yeah, it is plus. It's not able to be seen, but it is plus. From SWDW. Here I have shown you a gate example. Please go through this and pause this video over here. Else I have illustrated the solution for this video in this slide. There's one correction over here. It should be plus, as we can see that if we multiply minus of xt minus t naught to minus of xt minus t naught minus tau, it will give, the minus minus will give me a plus. So it should be a plus over here and plus over here. Okay, so yeah, it is a plus in this video. Moving forward, I have given you one more example from the gate examination. You can solve this and you can get the link of it in the below slide, the solution for it in the links provided. Let's go to the next topic, that's noise. What is actually noise? Noise is a thermal agitation that the atom in an electrical component will gain energy and move random in fashion. They will collide with each other which results in release of heat energy. This heat so produces corresponds to thermal noise. A thermal noise power can be calculated with the formula KTB, where K is the Boltzmann's constant, T is the temperature, and B is the bandwidth. You can see in the diagram that its power spectral density is spread across the whole spectrum. The stochastic property of white noise, we can term it as the white noise is analogous to white light, which contains all visible light frequencies. A white noise generally have a zero mean. It is unpredictable as the noise samples at different instant of time are uncorrelated. Assuming zero mean, we say that noise has an infinite variance. To calculate the autocorrelation and power spectral density of bandpass noise, let's take this example and make the noise bandpass from minus B to plus B, that is a bandwidth of 2B with a magnitude n by 2. With the formula that I have shown you earlier, we can calculate its autocorrelation function and the power spectral density which is equals to NV. Again, it is a rectangle, a square or rectangular signal, and on autocorrelation, that is on Fourier transform of that signal, we'll get a sinc function. Okay, this is a property. This is the mathematical formula to calculate Fourier transform of a rectangular pulse, which will give you a sinc function. The noise channel capacity. We have often assumed that as the noise increases, the channel noise also increases. But this is not the scenario. We can see that for AWGN channel, that is additive wide Gaussian noise channel, as bandwidth tends to infinity. However, the channel doesn't tend to infinity, whereas it reaches a finite value. C equals to B into log 2 1 plus S by N naught B. That is the mathematical formula to calculate the channel noise, which gives me a finite value for an infinite channel noise. With the transmission of random signal through the LTI system, this is the last topic that we need to discuss in this particular lecture slide. So continue reading at this point. The mean of output signal y of t will be equals to h of t when convolved with x of t. We know that mathematical formula of convolution is h of alpha into t minus alpha d alpha over a period from minus infinity to plus infinity. Earlier we have known that to calculate the mean, we have to take the expectation of that process. Here, on solving, we get the expectation of output signal, which is a convolution of transfer function and the mean. If the mean is a constant, then it will be only the transfer function. If a random process is WSS in nature, then output mean will be equals to the power spectral density of the transfer function at 0 multiplied by the mean of the input signal. You can see in this box what actually an LTI system do to an input x of t system. Moving on with the next property, that is autocorrelation of output signal. Here I have calculated. Pause for a minute and check it out. Moving on, this is the formula to calculate the output autocorrelation and the output power spectral density. To calculate the average power, which is often asked in gate examination, you can apply this formula. Here again I have shown you one more gate example. Try to solve it from the formula stated above. Let's look at its solution. The power spectral density is given by n by 2 having a mean 0. To find its variance at t equals to 4, With the help of this formula variance, as expectation is 0, putting that value in the formula for variance, we can calculate Rx of 0. We already know these facts, and by the formula for our autocorrelation of output noise, substituting these, we get this value. Okay, the option for this will be answer A. So friends, we have come to the end of this slide. I would suggest you to test yourself more and try to answer different questions. If you like this video, kindly subscribe to my channel. Put a like button. Hope to see you in the next video. Thank you.